Welcome to Do You Know series on semiconductor. I am Satyan Muniratinam. Many people ask me what's the difference between a CPU, a GPU, and a TPU. I thought this is a perfect way to start this program of explaining the difference with an animation. The central processing unit, or CPU, works as a brain of the computer that performs the basic operations. GPU, the graphics processing unit, is a specialized electronic circuit designed to render 2D and 3D graphics together with a CPU. Tensor Processing Unit, or TPU, is a custom-built integrated circuit developed specifically for machine learning and deep learning applications. Let's quick look at the computing timeline. The greatest invention is the CPU, which is a microprocessor consists of many transistors forming many gates and logic functions to be a processor. With the invent of internet, the data is exploding at an exponential rate. In order to manage and harvest the information, AI chips like GPU and TPU are born as part of the new generation of computing chips. When we say the processing units, it's all computing power. To teach machines to think like human, it needs a lot of compute power and data. So let's have a closer look at how each of these processing unit works and operates at a higher performance speed. Artificial neural networks is inspired by the way the biological nervous system operates in the brain. A neural network is a bunch of multiplications and additions on a millions of numbers is called matrix operation. Activation functions are mathematical equations that determine the output of a neural network. The function is attached to each neuron in the network and determines whether should be activated or fired or not based on whether each neuron's input is relevant for the model's prediction. Machine learning is the study of computer algorithms that allow computer programs to automatically improve through experience. Imagine that you are in charge of building a machine learning prediction system to try and identify images between dogs and cats. The first step would be to gather a large number of labeled images with a dog for dogs and cat for cats. Second, we would train the computer to look for specific patterns on the images to identify dog and cats respectively. Every image is nothing but a set of matrix of pixels that provides patterns of pixels and patterns of colors to predict the target based on the learning experience. Let's have a closer look at and how each of this processing unit works. As I mentioned before, neural networks is all about matrix operations and how each of this processing unit handles the matrix multiplications and additions. CPU handles the matrix multiplication in the form of scalar operation, and it can handle tens of operations per cycle. Going to GPU, it handles the matrix operation in the form of a vector, and it can handle tens of thousands of operations per cycle. But looking at the TPU, it handles the matrix operation in the form of tensor, and it can handle up to hundreds of thousands of operations per cycle. The MNIST is the hello world of neural networks, and it's a large database of handwritten digits that is commonly used for training various image processing systems. You can see few examples here. Imagine that we are using neural network for recognizing an handwritten image of the digit 8. The image is a grid of 28 into 28 grayscale pixels. It is converted to a vector with 784 values called dimensions. The neuron that recognizes digit 8 takes those values and multiply by the parameter values. the red line shown here. The parameter works as a filter to extract a feature from the data that tells the similarity between the image and the shape of 8. In short, neural networks require massive amount of multiplications and additions between data and parameters. So the problem is how you can execute large matrix multiplication as fast as possible with less power consumption. CPU is a very fast general purpose processor based on the von Neumann architecture. That means a CPU works with software and memory. A CPU has to store the calculation results on memory inside for every single calculation. This memory access becomes the downside of CPU architecture called the von Neumann bottleneck. Even though this huge scale of neural network calculations means that these future steps are entirely predictable, each CPU's arithmetic logic units executes them one by one, accessing the memory every time, limiting the total throughput and consuming significant energy. On the other side, CPU is so powerful because it can run millions of different applications just by changing the software. You can clearly see the time that takes for CPU to train the model. It's really slow. To gain higher throughput than a CPU, a GPU uses a simple strategy. Why not have thousands of ALUs, arithmetic logic units, in a processor? The modern GPU usually has 2500 to 5000 ALUs in a single processor. That means you could execute thousands of multiplication additions simultaneously. So it's a super efficient on applications with a massively parallel tasks such as the matrix operation. As you can see, both CPU and GPU read and write the intermediate result on memory at every calculation so that they can support a wide variety of different algorithms as general purpose processors. But this leads back to our fundamental problem, the von Neumann bottleneck. For every single calculation in the thousand of ALUs, GPU needs to access registers or shared memory to read and store the intermediate calculation results. Because the GPU performs more parallel calculations on its thousands of ALUs, it also spends proportionally more energy accessing memory and also increases the footprint of GPU for complex wiring. Google designed the TPU to build a domain-specific architecture. That means instead of designing a general purpose processor, Google designed it as a matrix processor specialized for neural network loads. TPUs cannot run word processors, control rocket engines, or execute bank transactions, but they can handle the massive multiplications and additions for neural networks at blazingly fast speeds while consuming much less power and inside a smaller physical footprint. With the introduction of systolic array architecture, the goal is to reduce the von Neumann bottleneck. Let's see how a systolic array executes the neural network calculations. At first, TPU loads the parameters from memory into the matrix of multipliers and adders. Then the TPU loads data from memory. As each multiplication is executed, the result will be passed to next multipliers while taking summation at the same time. So the output will be the summation of all multiplication result between data and parameters. During the whole process of massive calculation and data passing, no memory access is required at all. That's why the TPU can achieve a high computational throughput on neural network calculations with much less power consumption and small footprint. I hope this video gave some insights in the comparison between CPU, GPU, and TPU. Thank you for watching. See you next week with another semiconductor topic.